it's really great and honored to have Dr. KV Shajesh here to talk on our today's talk on the vacuum. So, maybe I will invite Krishna to introduce the speaker formally. So, Krishna, can you please introduce the speaker to our audience?
Okay, thank you, Jishnu. Just a second. Okay, good morning, everyone. We are very fortunate to have Professor KV Shajesh with us today to tell us a bit about his topic of research. Professor Shajesh is an associate professor at Southern Illinois University, Carbondale, the US. He obtained his BSc from Banaras Hindu University and his MSc from IIT Kharagpur. For his PhD, he worked at the University of Oklahoma in the US with Professor Kimball Milton, a student of Nobel laureate Julian Schwinger. Let me note that Schwinger had won the Nobel Prize in 1965 along with Richard Feynman and Shinichiro Tomonaga for work on quantum electrodynamics. The title of Professor Shajesh's PhD thesis was Casimir Effect, an Avatar of the Quantum Vacuum, which I think we can safely assume was a title that was chosen by him. This thesis earned him the Nielsen Prize for the best PhD thesis from the physics department. After his PhD, he has worked in Florida, New Jersey, and Iowa in the US, as well as in Norway. He was also a co-investigator of an international research project and Casimir effect and van der Waals forces in multi-layer systems funded by the Norwegian Research Council.
You got muted.
Sorry, you got muted, Krishna. Hello? Hello? Hello, Krishna? Hello? Krishna, can you hear me?
Yes, yes.
So you got muted at some point.
Yes, yes, yeah. So I'll continue from where I left.
Yeah.
So after his PhD, he has worked in Florida, New Jersey, and Iowa in the US, as well as in Norway. He was also a co-investigator of an international research project on Casimir effect and van der Waals forces in multi-layer systems funded by the Norwegian Research Council. He is a founding member of the recently started Swix Science Center in Thalasheri, which is a center for science activities with the immediate goal of connecting highly motivated, enthusiastic students with mentors using easily available online tools, which is a goal that KTPI also identifies with. I extend a warm welcome to Professor Shajesh and invite him to share his passion for the quantum vacuum with us. Over to you, Professor Shajesh.
Thank you, Krishna, and thank you, Jishnu, for managing this. I'll try to use the blackboard here. I should point out, so I'll speak a little bit of Malayalam and English. My Malayalam is really bad, but still I'll manage. I'll be using the blackboard. Those who are having the screen small, you can pin my video. That is the best way to get this. And I'll try my best to make it simple, and hopefully it is not too simple. That's the price you pay. Okay. Then in the quantum vacuum energy. So I'll be speaking on quantum vacuum energy. So, you can easily, I believe it can be said that this is a jargon for many of us, but still, let me try to explain what that is to begin with, and then kind of motivate what exactly some details about it. So let's begin by seeing something that we have all seen, and then so let's say charge, right? So this is either all of us probably know what a charge is. This audience should be perfectly fine to elementary, maybe. Charge comes in positive and negative. Suppose an atom under, so this is an atom, I'll simply say there is a positive and a negative. And if it is spherically symmetric, e positive and negative charge random almost symmetric, then it is reasonably neutral. So the basic idea is, or atom, is it neutral or not? and will it interact with another atom? If it is neutral, other atom node interact to so it is neutral, so I'm going to say charge doesn't exist. Then what is the property? Then the property on an atom that is participating in an interaction, and then we say, oh, that is a dipole. There is a chance that this positive and negative is not really symmetric, so that is slightly off, and that's what we mean by dipole. But let us also consider a scenario where the dipole is also not there. And then you would say, if charge and a dipole is not well defined, then it is possible to define an ambiguous quadrupole. But let's assume that this quadrupoles and all are zero. That's an assumption. That's not necessarily true. And higher orders are not there. So you can keep going 2, 4, 6, and so on. But we say that we're going to get this off. So now we have two atoms in this manner, who do not have a charge and do not have a dipole, and either this either atmosphere maybe this is compare this with minnal samayathu endana sambhavikkunnathu. So that is what I want to look at. So what is happening during a lightning? So there is a two neutral atoms, and what can you do about it? Let us say this creates an electric field. So if this has a dipole, then that will create an electric field. But there is no dipole. But if there are fluctuations, so notice I brought in the new term now. If there are fluctuations, fluctuations are disturbances. Disturbance karanam, and usually it is temperature fluctuations. So temperature fluctuations. And we are talking about atmosphere. Normal, we are speaking about mineral. So there are two atoms, and they can create, one can create an electric field, and due to this temperature fluctuations, these atoms can move around a little bit, and temporarily this polarizes. So that becomes plus, and this becomes negative, and now you have a dipole moment. Our dipole moment creates an electric field. Right? So that's an electric field that will polarize this, that is plus minus, and suddenly there is an interaction. Notice what is happening. No charge, no dipole, but there can be an interaction between the atoms. This is what is normally known as van der Waals interactions. And these are induced effects. So words used are induced polarization. So the basic idea is, even though an atom is neutral and having no dipole moment, it can still have electrical properties if there are temperature fluctuations. That's what we want to explore. In the worst case, we can also say, in the extreme case, let's say not the worst, let's say there is a positive and a negative charge. And if we exert enough electric field, if this electric field is large enough, that means typically E threshold is about 10 raised to 5 Newton per coulomb. After electric field, this atom will basically strip into two. This positive and negative charges will break away, and that's called breakdown of air. So breakdown of air. So do I need to mute someone? Let's see.
Yeah, I will be muting.
Oh,
It's
okay.
okay.
Yeah, you should be able to. Yeah. So if there is a threshold electric field of about 10 raised to 5 Newton per coulomb, you can actually break an atom, or atom breaking, and that is basically what happens during lightning. Lightning the electric field charges into, so then this will break an air molecule, and that's what happens during lightning. Now, the whole point is, this is all good. So this is all atmosphere. We are talking about an atmosphere and an electric field created externally. But as I said here, one could create the electric from one atom to the other. So that's broadly what we are talking about. So let me now switch the scenario. Now I want to bring in a vacuum. So let me change the board. Yeah. So now let me say, let me introduce the idea of vacuum. And first, let me say what is classical vacuum. So this may not be a standard, the standard terminology, but let me introduce it anyway. What is a classical vacuum? So let's say this is a space devoid of mass and energy. So I introduced two terms now, mass and energy. Very simplistically, mass is anything that is localized. That means to say a finite amount of space occupied. It is not infinite. And energy is any entity, any physical quantity that occupies infinite amount of space. So that will be the distinction. And if you have space that does not have either of this, neither a mass and energy, another simple way of saying this is these are particles. This is for an audience that we have particles, and this is field, like electric field, like any of the field, gravitational field, electric field, magnetic field. That's what we mean by energy. So that's what we have. And a classical vacuum is you remove all of this. With the full remove whatever is remaining as classical vacuum, and that's pretty much nothing. Right? But now we want to bring in some effect here. So we want to bring in the quantum vacuum. And what do we mean by that? So a quantum vacuum will be the classical vacuum itself plus, so that's the new thing, and plus quantum, the word is, and quantum fluctuations. So earlier I introduced temperature fluctuations. So now this is a new terminology. What are quantum fluctuations? So that's the key player here, and I need to motivate that a little bit. So what are quantum fluctuations? So for that purpose, let me first take a very simplistic approach. What it is have the normal vacuum, but now we have the idea that you can create matter plus antimatter. There is a chance that there is a matter and an antimatter suddenly appearing in space because of some fluctuation. Earlier, dipoles, the polarization was occurring because of some temperature fluctuations. Now we are saying suddenly that could be a matter-antimatter creation because of quantum fluctuations. And then just to have an analogy as to is this even possible at all or not? Yeah, experimentally, like we have never achieved the idea of creating matter and antimatter using an electric field. But this is a theoretical concept that if you have a threshold electric field of approximately 10 raised to, I think, 16 Newton per Coulomb, then the vacuum will break into a matter and or an electron, and a positron can be created using 10 raised to 16 Newton per. That's a really huge electric field, and we also need this to be constant, or constant electric field. It cannot be changing. Electric field does not do the job, and that's very hard to produce in a lab. Even a laser, which is not really constant electric field, has only about 10 raised to 9 or 10 raised to 10 Newton per coulomb. So this is not close to what we have. So, but the basic idea here is that was the analogy with lightning. I was saying that their atmosphere is breaking down. Here, when we are creating matter and antimatter, positive and negatively charged matter and antimatter comes in opposite charges, then we are basically breaking down the vacuum. And the moment you break down vacuum, we are creating a structure to the vacuum. And that's broadly what we want to say, but I want to come back to this quantum fluctuations. Why did that create that matter and antimatter? There was quantum fluctuations. So let me motivate that slightly in a slightly different manner here. So for that purpose, we should, or it is good to compare it with temperature fluctuations. So let me go back to this board here. By the way, any questions? Feel free to interrupt if there are any questions. It's a reasonably big crowd, but I don't mind getting interrupted if you're comfortable.
Yes, I have one simple question.
Sure. Yeah.
Can you hear me? Yeah.
Yes, please.
Once you put this intense electric field, it has vacuum.
Yes. Oh, what's the question? I didn't get it. If you put an intense
No, once there is an existence of an intense electric field in space, can you call that entity as vacuum?
No, vacuum is anytime there is no, that is not electric. If you have an electric field, it's not vacuum, correct? So the moment,
it automatically give you a E square integral E square.
Exactly, it's not vacuum. So the question is, if let us say there is a space here, that's a meaningful, and then the moment I put an electric field here, that's energy, right? Electric field is energy. So that's not what we have. So if we want to create vacuum, so think of, so this is a possible vacuum, like this is matter, antimatter. So matter, antimatter. You create matter, antimatter. You create matter, antimatter again here. So let's say antimatter, matter. And now this can interact. Like these are charged, positive, negative, and this has to affect that. So whatever is being
actually that was not my question. You were talking about creating what do I say, from vacuum
matter, antimatter.
Matter, yeah. So but you need to apply this much intense electric field, right?
Correct.
Once you put that thing, I cannot say it is vacuum. That's
it is not. I agree. I was just motivating it. That is not vacuum yet. I agree. So let me give me a few more minutes, and I will say that vacuum is you have to remove everything, devoid of devoid of matter, devoid of energy. By energy, I have removed electric field also.
Yes.
Right? No matter, no energy, but I will allow quantum fluctuations. Correct?
That I agree. That's
all I'm saying. That is all I will stick to. Okay. So rest everything is motivation for those who are not very familiar with these words.
Okay.
Okay. Is that okay?
Thank you. Yeah, that's okay.
Yeah. Sorry, maybe I'm making it too elementary and confusing. Yeah. So so let me proceed and I'll quickly get into this. So now, so again, quantum vacuum. So I'm motivating quantum fluctuations maybe now, right? So let me come to quantum fluctuations. Sorry, I'm hardly speaking in Malayalam. So hopefully, yeah. So quantum fluctuations, let's think of temperature fluctuation, and the best thing for that I feel one of the ways one can motivate is blackbody radiation. So energy associated with, let's say, one oscillator. I'll do this a little bit more mathematics, more formal here. So this is blackbody radiation. And typically it is a temperature related concept. And that has this idea that it is, let's say there are n oscillators of the same frequency. So this is h bar coming in. H bar is a Planck's constant. This is Planck constant with a 2 pi there. And now this is the new piece in here. And this is 1 over exponential of h bar omega over kt. Minus 1. This is what we typically see in textbooks. If I remove this 1/2, this is what we typically see in textbook, and that's what Planck did in his 1900 proposition that blackbody radiation can be explained and using this. But now what we want to take is that if we start from here and use the idea that h bar omega is very much smaller than kt, that means, so h will be a measure of quantum fluctuations. So there are, if temperature fluctuations are very large, okay, then your energy takes the form. So this is approximate, or this is equal to, right? In the limit, when this is very large, when t is very large, this is very small. I can expand this about the exponential 1 plus whatever is in the argument of exponential. 1 cancels out. So you have kt going up. So you have n h bar omega. So there's 1/2 plus kt over h bar omega. This is anyway very large. So this gets killed over, and this is equal to nkt. So that's temperature fluctuations when temperature is large. But there is an opposite limit, and this was given by Planck himself. The Planck energy, I don't know, that is 1913 or something later on, not in 1900. Later on, he did this, and in that case, this is equal to, now h bar omega is large, so this is very high, exponentially very large, so 1 is negligible. This can go to the numerator. That becomes an exponential of negative of a very large number. That goes away. So this whole term doesn't contribute now, and we have n times half h bar omega. This is often popularly said that if you have an oscillator, if you have a universe which is completely empty, for each frequency you have a ground state of the energy. In quantum mechanics, you say that the ground state of a harmonic oscillator is half h bar omega, and that's what the energy is. And if you have all the frequencies, you have to add that all up, and this is often referred to as 0-point energy. 0-point energy in the sense that temperature is going to 0, but still there is some energy left. Remember, now we are talking about, so now what is quantum vacuum in this context? So quantum vacuum is, you have a cavity, like think of a blackbody cavity. Similarly, we have a cavity, no mass, so devoid of a cavity, devoid of mass. So no mass, no energy, and energy. But we have quantum fluctuations, okay, with, right, plus, right, quantum fluctuations. So basically some disturbances which are intrinsic, very intrinsic in our system that we cannot avoid, but we surely know it is there because all the experiment seems to suggest that there is such a background out there. So that's quantum vacuum. Any questions at this stage? So that's my basic point here, and from there I will move on. Okay, so what can we do with this? Maybe I should repeat that in Malayalam. നമ്മളെ അടുത്ത് ഇപ്പൊ എന്താ ഇല്ലതെന്ന് പറഞ്ഞാല് ഒരു cavity എടുക്കാം. Cavity is basically ഒരു electrical conductor or gold closed cavity എടുത്തിട്ട് remove all the masses, എല്ലാ masses അതിൽ നിന്ന് remove ചെയ്യുക, energy remove ചെയ്യുക. Energy is electric field or magnetic field or gravitational field, so the popular ones. Remove all of that, but we are still remove chedalum, that is having something which is called the quantum fluctuations that we cannot avoid. And to dominate, if we want to make the quantum fluctuations dominate over temperature fluctuations, we would like the temperature to be really small, and this is extremely small. That has to be almost zero temperature for all practical purposes. So that's what quantum vacuum is. Now what we can do with
So,
this.
Shajesh,
Yes, please, question.
can I? So you talked about how these are verified experimentally, right? Quantum fluctuations. So could you tell us about some experiments where we can see that these fluctuations exist?
Yeah, okay. These fluctuations exist in the sense whatever quantum mechanics we are seeing, right? That is being explained using the idea of H bar, right? In that sense, they exist. But if you ask me in the quantum fluctuations in the sense of temperature, can I see it? Can I test it? Probably not. Like, can we have a real proper direct evidence that this half exists or not? I would say that will be debatable. Like, one might debate that has been done or not. Like there are sufficient articles written that even Casimir effect that I'm going to talk about, whether it is really a manifestation of 0-point energy. The way I am going to portray, like is that Casimir effect is an evidence or manifestation of this 0-point energy, that is this term. But you will hear literature, or at least a small part of literature, saying that no, this is not a direct evidence. So when I said that, yeah, quantum fluctuations exist, the whole of quantum mechanics, we know that there are quantum effects, and quantum effects means that there are quantum fluctuations at deep level, or that if there is thermodynamics, that means temperature exists, and then temperature fluctuations is a consequence of that. In that sense, I meant.
Okay, but you do believe that Casimir effect, which you are going to talk about, that is an evidence of 0-point energy.
Correct, exactly. That is how Casimir portrayed it, and Casimir effect has been experimentally observed. So that is the point. So Casimir effect, the way it is interpreted by most of the theorists, is a manifestation of quantum vacuum energy, and that has been experimentally verified. But that doesn't mean that we can, it is immediately possible to get energy from that. That's not what we are saying. Right.
Okay. Okay. Yeah.
Did I clarify?
Yeah.
Excuse me. Can I ask you something?
Yes, please.
Can you take the same point of view for lamp shift also, or?
Can I take a same point of view of what?
Lamp shift.
Oh, yes.
Contribution.
Yes. Yeah, of course. So lamp shift is purely quantum. Yes, of course. Yeah, like quantum field. Yeah, that's a quantum electrodynamic effect. Of course. Yeah.
So that.
And maybe I can elaborate on that. Like in the whole of quantum field theory, if you're familiar with quantum field theory, when we say that there is a transition amplitude, vacuum to vacuum, like when we write this, right, that probably this notation is familiar, right? This is the transition. So this will be vacuum to vacuum transition amplitude, right? That's the starting point. That is the starting point of field theory. Oh, I had to move this camera a little bit. Yeah, that's the starting point of field theory. And that's what we're talking about. And here, typically, there's a source there. Let me write that. I'll talk a little bit on that, right? And yes, so anytime we are doing quantum field theory, yes, we are presuming that there is a vacuum and all these fluctuations exist. Correct. Yeah, so and Lifshitz is a quantum electrodynamic effect. So yeah, surely that's a indirect evidence.
Yeah, that's what I was asking is in the case of Casimir effect, you said there may be a point of view, whether it is a true
correct
vacuum effect. But in this case, can you, if we have, do you have any other choice?
No, probably not. See, there it is. I think that is the only choice. Yeah, I think quantum. Yeah, there I think. See, the main problem is that this is a divergent quantity, right? This half h bar omega, right? This is like when we say there are, like I'm going to talk about two parallel plates attracting. Is this necessarily coming from this? That's probably what everyone is saying. It's convincing to me that it exists, but probably I can appreciate the criticism that is there. That's the way to put it.
Okay,
but I will agree that Lifshitz does not belong to. Like here we are talking about this half in there. Is that necessary or not? Yeah.
Maybe you can say that Casimir effect is the field theory in the presence of classical background, and alternative explanations are there to explain whatever is observed.
Yeah.
So that's the criticism one can build up on. And experimentations that have been done, they are done with materials. It's not a pure vacuum experimentation that has been done. So in that sense, the Casimir effect, the original Casimir effect, which was done using the 0-point calculation, has not been verified. The Lifshitz theory has been verified. And I guess that's where, like, I mean, yeah. So unless like it is pure vacuum and you can actually show it.
Yeah. Hopefully I will be able to convey that better few minutes down the line when I've introduced Casimir effect. I haven't introduced it. So if you allow me, give me a few more minutes. But thanks, Prachi. That's a good comment. Yeah. Did that help, and can I proceed? Yeah, but good questions. Yeah, thank you. This surely helps. Yeah. Okay, so and it is half an hour now, right? So yeah, I think let me give a bit of a mathematical description, because there were reasonable questions. I think this might fit in. This is again a very simplistic model, but the same idea here, just to give you a feel of what, like typically always you will say that there's a harmonic oscillator, that's a ground state, that's a bar omega. That's okay, perfectly fine. But let's do this a little more with this vacuum amplitude that we had. So let's have a simple scenario again. This is a wall, that's a frictionless ground. And let's say there's a spring and there's a mass m there. So that's mass m, there's a spring constant k. And let's say we are forcing this. So this is a forced harmonic oscillator, and we know that Newton's law would say that mass times acceleration. Let's say everything is in one line. There is mg and normal force acting, but the actual motion is in the x directions. I'm not writing the vector there, so that's minus kx plus f of t. So immediately second derivative, so here m second derivative dt squared plus k, that's x of t, and that's equal to the forcing function. And now what we want to talk about is this f of t is not really a normal, typically we would say having a sinusoidal oscillation. This is random. Let's say this is random. In fact, if we want, now that we have introduced quantum fluctuations, these are like quantum fluctuations, purely random. There is no control on that at all. If we have such a system and we want to talk about what is the energy associated with this system, we would say, and before I proceed into the energy, let me introduce one more term. So this is the same, this is an inhomogeneous differential equation. So to solve that, you would introduce a Green's function, right? This, when we are doing mathematics, that's pretty much just a assistance or a methodology to get the solution, but here it will become physical. Notice, so this is Green's function. So this is Green's function. I'm squeezing it there so that I have the space there. So that's Green's function. All that very elementary. And now let us say that x of t is 0 on an average. This has more formal definition in terms of the vacuum to vacuum transition amplitude and so on. The quantum feature there. And we are going to say that in the limit f tends to 0, this this average of these fluctuations is actually 0. Right? That's perfectly fine. That is understandable. We can think of it as on an average that mass is not moving. So that's equal to 0. But the quantum correlations, the second, or think of it as x square. If x is 0, it doesn't mean that x square is 0, right? Because x square is all positive. So positive numbers do not add up to 0. So even if this is 0, surely this need not be 0. And give it a time dependence in there. So this is not equal to 0. In fact, we will say that this will be equal to, this can be shown, it is not really an assumption, this can be shown that this is equal to the Green's function. So I won't show that here. It's a little bit like few steps. If I define those things, if you have more time, that can be easily done in an introductory course. Right? So this is what is called quantum correlations. So that's at the heart of this quantum correlations, which is basically the idea of quantum fluctuations. Again, simple harmonic oscillator, reasonably elementary. There's a Green's function. And now let's talk about energy associated with this. So energy would be, let me use E, not using Hamiltonian or anything, just for simplicity. So let me just explicitly write it. Energy is equal to half mv squared. Let me write explicitly dx by dt square, velocity square, like motion, and the energy stored in the string. So that's half kx squared. So that's a time dependence in there, square. And there could also be an energy associated with f of t. So then this you would say this is f of t times x of t, like position times force, if you want. This now we want to, like, that's your energy simplistically, but now the way I want to write this is 1 over 2m d by dt. Let me write it as partial. So that's d by dt prime plus half of k and let's say x of t times x of t prime. That's fine. Fluctuations coming in, and now I've introduced 2 times here. Take the limit t tends to t prime. So this is a formal way of doing whatever we said earlier, and this is a Green's function, remember. So that's your Green's function, and this again with a little bit of effort we are to get the Green's function and so on. So this comes out to be exactly half h bar omega. And what is omega? I should define my omega there. So omega is k over m, square root of k over m. And this is basically at the heart of the quantum field theory also. If in some form or the other, this is how we incorporate quantum field theory in a more complicated structure or configuration, but a very simplistic configuration has this feature. But the only difference is we are setting this f to be 0, right? So what we are saying is that if we first put in all the particles and then we remove all the, like we want to remove everything out, and that's the idea we are putting in. So with all this, this is the background. If you want, this was already
Before
yes.
you
Please.
proceed,
Yeah, please.
I just want to make sure you have this correlation function xt prime, right?
Right.
So how the h bar is appearing, because you have assumed these fluctuations are quantum t.
Yes. Okay. How? Okay. That is actually, yeah. That is the, yeah. What you would do here is that.
No. Just tell me. That's enough.
Yeah. This is by hand. So this is I will say Schwinger's, like when you do, like when we write this equation, and when I go to energy, that is this Lagrangian action principle, right? Here we will do Schwinger's action principle, right? So that's where that when we say action principle, it becomes a postulate, right? So the change in any change in the vacuum to vacuum transition amplitude will be equal to 0 plus, and any change in the action, so this is energy if you want, it's the Lagrangian, right? That's the action, 0 minus, and here there is this IH bar. That's your H bar. So when I do this, typically in classical mechanics, you would say only the action there, change in the action is what is there. But when we do the quantum action principle, we put that H bar in there by hand. This is a postulate if you want. That's where that H bar came in. But that's a very good point. The way I introduced it, this appeared from magically, right? So that in a more formal way comes in here. So this is the seed of that quantum fluctuation.
But there's a classical analysis where you have Langevin equation and relate correlation function.
Yes. There it will be pretty much replacement of this KT, like we have this temperature. So there the fluctuations itself is associated with the H bar. Yes, that is also okay. Yes. So when you write the Langevin equation, basically you're postulating again there that this is an H bar or KT, right? If this was a polarization, then you would say that is a KT there. Yeah, either I say that's okay to my understanding. Like I don't use Langevin equation so much, but I would say yes, that is that's okay. Yeah, I don't have more comments on that. Yeah.
Okay, that's okay.
Maybe
no, I just want to know how H bar suddenly here. So it is through this correlation function you are introducing.
Exactly. Yeah,
that's okay.
And as I said,
guess you might know it
derived,
as
right?
Shajesh, you might want to say like they might know it as quantization, right? Like you quantize the theory, like you have a classical correlation function and you quantize the theory. That's where you introduce the uncertainty and include this H bar.
Does that help?
Now, what is the quantization procedure you have in mind?
So basically in the quantization
quantization
principle we have is the commutation relation, which is set to the 0 in classical picture, but then you quantize the theory, so you introduce the uncertainty. That's where you introduce your H bar.
No, I mean standard wise you have two canonical variable, xp is equal to IH bar. Of course, you can use
yeah, so if you are already having H bar there, it is already quantized, right? That's the uncertainty.
Right, that's not the point. My point was, if you start with this X equation, right?
Yeah.
Your harmonic equation post F.
This is an input.
You can write down correlation for xt and xt prime from this equation itself. Then you end up with correlation of ft. Right?
Yeah, that's
so some quantum nature of ft correlation also can give you is same thing. That's what I want to know.
Yeah. So the way,
Correct.
yeah, you're correct. See, the way we see it is that we say, when we say Casimir effect, that there could be a correlate or fluctuations in the dipoles can lead to the same effect. So yes, I think that is okay. You can have a correlation in this f of t being 0 and f of t times f of t prime being postulated as having an h bar over something. I cannot say exactly what it is.
Yeah, I agree.
But
Yeah.
that will also give you the same thing. But I haven't immediately done it, and I might not be able to reproduce it right away. I'll have to give it some.
Yeah, that's fine.
Yeah. But I agree, and we think of it as dipole fluctuations in dipole versus the fluctuations in electric field. So yeah, correct. Yeah. Okay. Thanks. Yeah. So there's a good point that this H bar is flying, just came from the sky. Not there. I'm just saying, yeah, it did come from a postulate that, and that is the action principle of Schwinger. We say it's Schwinger.
Sajesh, maybe I can also share my own confusions
Yes.
in the same associate. So it's roughly because you in the right hand side, the f of t is a random force. So how do you say it as a classical stochastic random force or quantum random force?
Classical. This will be a classical stochastic force, at least in this way of formalism. Now, Langevin might say it differently. I'm not sure, but the way I am seeing it is that this is completely classical. This is a classical stochastic, or which has the quantum features of quantum fluctuations in it. And remember that we're going to set f going to 0. So eventually we want to remove that. So even then there is a remaining effect in there. That's the point. So
Okay.
So and it plays an important role because see, there is this quantum effects has to stay inside this, mathematically speaking. Quantum effects has to stay inside this brackets if you want. Others can get out, right? So that's the main, at least mathematically speaking, that helps. Yeah, maybe did that?
Yeah, got it. Yeah.
Yeah. So okay. So with this, I think so. Casimir had all this while this is in 1948. I think Casimir had all this input. Or I believe that he had these things in his mind, and he came up with this idea that if you have electric field now, on an average that is 0, right? But electric field square, right? Let me not write it as a square. So there is 2 electric fields. It's a dyadic basically, or it's a tensor, right? Outer product of this. This is not equal to 0. Again, this will be equal to the Green's function. Now it will be a tensor there, but let me just say that that is not equal to 0. That's good enough. And he could derive that if you have 2 plates, 2 parallel plates, right, so these are of infinite extent, the distance between them is a, so these are conductors, the perfect conductors, perfect electric conductor. And let's say temperature T is equal to 0, and what else? And there is no charge, right? No charge. So we have conductors, but it's absolutely no charge. So there should be no electric effect, electric force on this. But Casimir pointed out that there will be a force on this. Let me write the energy first. So this is energy, but these are of infinite extent. So we have to talk about energy per unit area instead of energy itself, because energy is large, area is large. And this is minus of, there is an h bar that shows up, c that shows up, the speed of light, and there is an a cube, the distance between the plates, and there is number. That's it. Very neat, very simple result, and that's an exact result in the sense. But there is this 2 boundaries. So there is this full vacuum here, quantum vacuum, But now you have two boundaries, right? Two boundaries you have put in. This is a conductor, and if you want, this can be half slab, or if you want, you can make it very thin, and that's perfectly fine. Either way, you get that result. And these are now classical boundaries, like classical in the sense that it is perfect conductor, so there is no effect on this, like effect in the sense this cannot move, but this can make the field can get affected by this, but the field is not going to affect these planes. And pure perfect exact result, non-perturbative result, you cannot get this as a perturbative quantum field theoretical perturbation doesn't give you that. But if you sum up all the loops in there, that gives you exactly this. And a simple, just an A cube there, H bar and C, very clearly saying that this is a quantum effect and a relativistic effect. And the force per unit area is basically negative with respect to A of energy per unit area. And that comes out to be pi square over 240 H bar C over A cube. This was Casimir's result in 1948. He noticed before 1948, there were precursors to these results, almost like van der Waals effect, like they talked in terms of two molecules attracting. And there the idea was related to the question that came up. So there is this dipoles in here. So each of this, so you think of this now as two dipoles. In that case, I have D of T, the dipoles, that's equal to 0. Or I can have correlations in the dipoles, that comes out to be the dielectric constant. That's not very obvious. Let me just say that this is not equal to 0. So either you can see this effect as due to the fluctuations in the dipoles inside the plate. That's one way of deriving it that can be done. Or you can say that electric field, which is inside in here, that's a vacuum here, that's actually having correlations not equal to 0. This is what Casimir preferred, and the famous story is that Casimir had this result related to atoms, which involved the correlations in the dipole moments, and he had a discussion with Bohr. They went for a walk, and he was asking suggestion from Bohr, and Bohr, the statement of Casimir is that Bohr mumbled that this might have something to do with 0-point energy. And immediately, within few days, apparently Casimir got into the right line and he could derive this result, which is very straightforward. It's only about 2 pages. A very simple result, but profound in the sense that immediately now you're saying that that's in a sense you're trying to indicate this is a manifestation of 0-point energy, which the way I stated probably not very obvious, but that's so that's Casimir effect. If you want any questions at this stage. Okay, good. So let me see what else I can. Yeah, let me do one more thing. I have about 125. Can I take 10 more minutes, Vishnu?
Yes, please. Yeah, you can.
So it's about 5 minutes left for 1 hour, but yeah. So let me. I think a few things might help just in the context. I won't do too many things. So one is. I should say about the experiments related to this. Right, so experiments related to this, right, 1948 that was proposed. 1958 there was a attempt on this by Sparney, I think, maybe Sparney, right? And this had an error of about 100%, so it was not very conclusive. There's a 100% error, but still it was not a null effect in a sense. And then came 1997, it was Lamoureux. spelling again? I don't know. I'm spelling. I'm wrong. Maybe. Let's see. Do I have it here? I should say that correctly. REAUX. EAUX. This basically used a torsion pendulum. Like on a sphere. And this got an accuracy about 20% accuracy. Oh, maybe I should also have point out that this force, if you want any reasonable force with this, maybe I should point out that force there, right? So this force here, if you want, if let's say h bar we know is, this is pi square over 240, h bar is about 10 raised to minus 34 in SI units. Speed of light is 10 raised to 8 meters per second in SI units, divided by a cube. Like if you want anything reasonable out of this, this is force per unit area, that's 1 atmosphere. So just if you see that it is 10 raised to minus 9 meters, that's a nanometer, right? An atom is about a 0.1 nanometer. So that comes out about 1, right? Approximately of that order, like then this is 1 atmosphere. So that gives you an idea that you have to really go small to get these effects large, but it gets really large, very quickly gets large because this is a cube effect. So that's yes, Krish.
Actually, a fourth.
Oh yeah, force a raised to 4. Yeah, then does it change? Yeah. Okay, help me here. Okay. 34, because when I was doing it, I did cube, I think. So that's 26. Yeah, that makes it very large then, right? So maybe I need less then. So it is 10 raised to minus 8 is sufficient. Yeah. So, right, 8 into 4 is 30 minus 36. And this is, yeah, so maybe
About 100 nanometers, right? So
yeah, typically the experimentally, yeah, from our knowledge, we know that this is about 100 nanometers, this backend starts getting affected. Like if you want small, like 1 micrometer is small, then the force is really tiny. But as you get smaller, it very quickly picks up. And within that, typically we say 100 nanometer, but then I think before the talk when I was doing, I was having the cube here. So then, so yeah, so let me, not a very good calculation there. Okay. So I think 10 raised to, let's see this, let me do this, minus 26, 432, so that's 10 raised to 6 already, right? And that is a 10 raised, so it's about 10 raised to 4 Newton per meter square. That is 4, I said. Something like that. I think if I did that start, approximately at least. Okay, sorry about that. Okay, so if with that feature, that yeah, it's still, I think I convey that that's an atomic length. I should also say 1998, the experiment done by Mohiddin. This became very, so this used AFM, atomic force microscope. And this came with an accuracy of less than 5%. In fact, even better, I think. But then one should be careful, one should interpret what other things are going on. So that's, I think I should say that so that we have a clarity of what's the status. So since 1998, there has been a real boom in there was a lot of trust in this, and I mean, now they really talk in terms of applications, how we can build nano machines out of this. The main idea is that whenever you build something small, like if you're thinking of a micro mechanical machine, everything sticks. Like because of this Casimir, everything sticks. And the main goal then is how can you make this repulsive? So that was a very serious challenge. And then in 2010s, there were proposals as to how you can make this, basically make a hole. Like the simple solution is that if you want to make these effects repulsive, if you have a simple plate, make a simple hole there, and in that tiny region, there can be a repulsion. So I'm just motivating that. So that's a keyword you want to keep. I won't be able to tell the details in here. Put a hole in a plate, and there can be some form of repulsion in there. But instead of talking about that in more detail, let me, in the very end, give a toy model of how you can motivate this in a very popular level. So let's think of a harmonic, like a guitar string, right? So we have a guitar string. So that's a guitar string, but the condition is that at z equal to 0, that has to be 0, and at z equal to a, that has to be 0. So that's the only condition we put. And if you have a string have an oscillation, so this is d squared by dz squared. This is again the harmonic oscillator coming in, and this is plus omega squared times phi of z has to be equal to 0. That's a equation, we can say a wave equation, but it's a Fourier transformed in time. And we also put the condition that phi of 0 has to be equal to 0, and phi of a has to be equal to 0. Phi of 0 has to be equal to 0 means that only sine functions can contribute, the sine functions cannot contribute, and phi of a equal to 0 immediately says that the omega there is any omega will not work. It has to be n pi over a. And actually, for dimensional purposes, we also need the c, right? C square. Right? So there's a 1 over length squared, so I need a c square there. So omega n over c. So this is a pi c over a, where that's and where n has to be equal to plus or minus 1, plus or minus 2, and so on. So if we simply say the total energy to be the sum of all these modes, I'll just add up all this n and half h bar omega, right? So that's my understanding of vacuum in the sense we have put it. You have all these possible oscillations in a guitar string, but then you want to think of a situation where all the modes contribute with equal amplitude, right? All the energy associated with all the modes with equal amplitude, all the way from 0 to infinity, and that's equal to 1 by 2 h bar omega n is pi c over a, and I have to add these numbers, right? 1 plus 2 plus 3 plus so on. Now that's a hard series to add, but more recently in YouTube, there is which has the things that have gone viral. I will use that, and actually this sum of these numbers which are positive and divergent turns out to be equal to minus 1 over 12. Very surprising result, but using analytic continuation, it can be done. But if you use field theoretical methods, we go along a different path and get exactly the same result. So if you have a single oscillator and having the same features of a quantum vacuum, so this will be equal to 24A times pi. So this is one dimensional. There's only one oscillation in one dimension. So the Casimir energy associated with such a string would be 24A. There's only one length there instead of a cube. With that, I think I pointed out sufficient things. I suppose I can speak more, but I think I should stop. So I've already crossed 5 minutes there. I was expecting a 40-minute talk. So yeah, I will say I'll take questions at this time. Is that okay if I stop, or do you want me to continue? Yeah.
It's fine. We can stop here.
Yeah,
So
sure. Thank
maybe
you.
thank you, Shajesh. So maybe we can take a couple of questions about the talk. After that, he's willing to take some question regarding career opportunities and etc. So okay, so unmute yourself and ask your questions.
Yeah, Professor Shajesh, so you're talking about people looking at applications for this Casimir effect, right? So could you say a bit about what is the update on that?
Yes.
There are efforts going on.
Yeah. So there was a recent experiment. I think. Okay. First, maybe I should say what's the nice result recently was that. So the nice result recently was that if you have a plate and you have a tiny hole, so this is a flat plate, conducting plate with an aperture in it. Let's say the radius is A. And along the axis, if you keep another metallic object, let's make it anisotropic. You can say this is an atom which is anisotropically polarizable. Remember, it has to be neutral. It cannot have any dipole moments either, but it is polarizable. It can polarize because of these effects here, because of the fluctuations in this. And we want to keep it anisotropic, so that's a little long there. And if you say this is height h, right? So it turns out that if height is greater than about, I think it's about 0.6 A, that's attractive. And if it is less than 0.6 A approximately, this is repulsive. So the main idea was that if you want to do anything with tiny objects at a microscopic scale, that means at a let's say nano materials, then you have to avoid this force. And then main idea is make holes. If you make a lot of holes, then that is possible to do that. And recently, I think 2-3 years back, there was a zipper, right? We think of zip like a zip, right? That is used to open. How do we draw this stuff? Right. So you have this zip that can come and close into each other. And the main idea was that you could do this at a nano level using this mechanism where an object was coming in and it could actually move and this will split into two. So that that was sort of, if I understood correct, this was a Nature paper, and then it was done in Singapore by Chen, I think Chen et al. And they could do that. Maybe Prachi can elaborate on that. Prachi, do you want to elaborate on it? Did I say that correct at all?
Yeah, I think they are making some kind of device which was etched on the single structure instead of mechanically moving parts. So I'm not exactly sure of it, but yeah, if you want to look for advances, I'm going to give you a popular article that you can see on Physics Today.
Yeah,
it's in the chat. Oh, I'm sorry, I think I didn't send it to everyone.
So yeah, so that's a, I mean, maybe I can just say that maybe that, I mean, in nano machines, that is one thing. And maybe I can also say, I mean, this is all sounds like, oh, it is not realistic at all. Come on. I mean, if you're not interested, going to make nano machines, we cannot do this. But we found a very interesting scenario. I shouldn't say we, I mean, there was a effect that was talked in 1991 by, what's the name? Okay, let me explain this. So the idea is that we said, if you have a sphere, right? This is ice, and now there is a possibility that, so this is water, and this is vapor. And let's say this is, we are at triple point. And now you could say, if you're at triple point, there is no energy needed to go from water to vapor, right? So there is a choice of how thick this layer could be. So the question we asked is there any thickness of water on ice by some fundamental reasons? And we said, okay, because it's a triple point, there is no reason for it to be having any thickness. But let's say we talk about the Casimir energy of ice, water, and vapor, and we said that there will be actually a thickness of water on top of this, so which is about 3.5 nanometer. So this D comes out to be about 3.5 nanometer, which yeah, experimentally there are difficulties with doing this. So you want to take it with a pinch of salt. There are like what kind of dielectric functions we use that matters into this, but that's an analysis one can do. So that's realistic, very realistic. And I should point out that for the flat case, this was already done in 1991. I don't remember the name of the authors right away from my head. So that's another application. So it does not have to be nanotechnology, but yeah, in that regime, right? Again, 3.5 nanometer. Is that a reasonable answer?
Yes, yes,
for
of course.
applications?
Yeah, that is, yeah. Thank you. And do you have any comment on your ongoing research, like what you're trying to?
Yes. So recently, yeah, we're doing few things. Like the most current is that recently our one of my student, like I would say in the last many years, he might be there in the audience. He actually, instead of taking this as a plate, he said that even if it is a ring, that shows the same effect, and we could get analytic results for this. And all the answers we have got until now was on the axis. It was not possible to get it if you go off the axis, just because it is tedious calculations and no one did it. But we actually went beyond the axis, and we are wondering if this can be stabilized by any chance. Our idea is that if you rotate this, spin this, can this be stabilized at all or not? So that's why we had to have the energy beyond the axis, and our goal is to see if that stability is possible or not. We just got the results off the axis, which we haven't sent yet. So after that, we need to do the stability analysis. That's one thing that is going on. The other thing is, yeah, Venkat here, he's in the audience. I had seen him earlier. He's in NIT Trichy. He is working on the idea that if you have an electric conductor here, and on the other side there is a magnetic conductor, then it is known that this is repulsive. In one case, this is attractive. Electric is attractive, electric magnetic is repulsive. But he has this very interesting result of if you introduce a new quantity in between, the electric magnetic can get converted into electric. So I think it's a very non-trivial and very neat result he has derived in the last 6 months. Again, it's in the process. Hopefully in the next 2 months or so we will communicate it. So that's two things that is going on. So yeah, mostly around Casimir effect, but come up with some clever things that we try to tweak the existing ideas into Casimir physics. That's mostly what I try to do. Yeah, hopefully that helps. Yeah,
Thank you.
Yeah, thanks for asking these questions. Yeah, more questions?
Yeah, these are all numerical simulations or analytic?
Most of what we do is analytical. Now, when does it become numerical? Is that eventually, so suppose we are doing this 2 plates, correct? So this is 2 plates you do. If we are taking perfect conductor, that is what Casimir did. And even if I am doing, I will immediately take it to a perfect conductor. In that case, it is tedious, but one can do it analytically. But somewhere, if you're wanting to connect with real life, for example, when you're doing ice, water, and vapor, then you need the dielectric properties of this. So this is the refractive index if you want. So the optical properties of this are refractive index, let's say N. So this is refractive index. And we need so this is refractive index. And we need the frequency dependent on this. Not only for the visible light, we need it for infrared, ultraviolet, everything. And that's the challenge, that it is not easily possible to get it for the whole range, and how much error there is associated to that. So, but once you depend on that, then it has to be numerical. So the moment you say this is realistic in the sense that it is frequency dependent, polarizabilities are involved, then one has to be numerical. So the final expression we have analytically, it's in terms of an integral, one frequency integral at the end. We use numerical techniques, especially for this. This was a pretty elaborate numerical technique. That was the first time we did, and then these things do not converge very well, so you have to use uniform asymptotic expansion. So it was kind of a neat numerical thing that we used to get that. So yeah, so we do numerics also, but limited. All that, because analysis is easier when you're in the analytic regime. So that's our idea. And another place where analytics becomes easy is when you take long distance when we call it the Casimir polder effect. In that case, the frequency dependence completely goes away and it is static. It's only the zero frequency that contributes. So that makes it a little simpler to do analytically.
How about this keeping it in the off-axis position with the hole? That also analytic or numeric?
This one, yes, this was analytic. Actually, this is in
off-axis.
So this is 2010. This was done by I think Levin et al. When they did it numerically. Like Levin et al. Did this numerically, but we actually immediately came and we kind of were not getting the result. But then we I think in 2012 we got an analytic version of this, but for dielectrics. So we did it analytically, which is having a lot more nicer because then you can analyze things much better. So, but this is they did it for a conductor and we did it for a dielectric. So at the price of not being
that was still on axis, I think.
Yeah,
the question was for off axis.
Yeah, we were on the axis at that time, and now recently, like I would say 2022, hopefully, is that we will be able to get off axis in terms of elliptic integrals. Yeah. So yeah, so this is possible to do these days for real materials, dielectric materials, analytically. But if you want to do conductors, that's you asked what are the projects we are interested in. To get an analytic expression for a perfect conductor interacting on the axis, that's still an open question.
Off axis or on?
Yeah, go ahead.
Off axis you can do analytically, that's what you're saying.
Correct. Off the axis we can do analytically and using elliptic integrals. Yeah. We can.
Yeah, but if you want to calculate elliptic integral, you have to do so.
True. Agreed. That is where
finally you need a computer, right?
Yes, we do use computers. The main challenge in all this, maybe I can say, see, we don't hesitate to use computers at all. We would be glad to use computers, but most of these calculations are divergent to begin with. They're all infinities. So and if you put an infinity on a computer, it will scream. It doesn't like it, right? So the main idea is to separate the infinite, and that's that experience that comes in. Otherwise, yeah, why not? I mean, numerical is perfectly fine. One can analyze it there. But once the divergence is removed, then we are good. Then it is a matter of taste, how much analytic you want or how much numerical.
But there is a unique procedure by which you can remove infinities, or because removing infinity can be a problem sometimes.
Yes, it is. It is a serious problem. And the main thing is, one can use, so this is regulation. This is regulation, it's not a renormalization. So one can use their favorite approach, but we have to make sure that whatever approach we use, we get the same answer, which can be challenging. But another way of motivating that issue here is that if we are doing force, that will be independent of these infinities. The force comes out to be always independent of this infinity. So
because derivative of a constant.
Exactly. Derivative of an infinite constant. Yeah, I agreed. Exactly. So that's one way of avoiding it. But often we work, like for example, this ice problem, we work with energy there. Then it is tricky. I mean, one can criticize, and I would say if we are not very confident with other sample or other places there where we have work, that confidence can be very less if you're just first time seeing it and it's in the jungle there, and it can be tricky. Yeah, but I trust them. Like I trust the results, but true. And I wouldn't make any opinion if a new person comes in and says that, no, I don't believe all these things. Yeah, they should not believe it. That's my take on it. It is dirty.
Thank you.
Yeah. Thanks. Yeah. Good. This was very nice. Nice interaction. Yeah. Any more questions?
Oh, so something fundamental. So when Casimir he took the fluctuation in the electric field, that was because the electric properties were infinite on the plate.
No, the distinction was that, or maybe you want to repeat that, electric properties were what?
Infinite on the plate. I mean,
Infinite.
the dielectric constant was infinite on the plate.
No, yeah, the dielectric response was infinite.
Yeah. The response function is infinite on the plate, and so that's why the fluctuation is in electric field.
No, that's not the reason. Like I would say that, okay, maybe the way to see it is that we have two plates. Let us say there is a fluctuation in here. If there is a positive and a negative, if this fluctuates, this oscillates, very simplistic way of seeing the fluctuation is this is oscillating, that means the electric field here will fluctuate, right? If I change this up and down, this electric field will change up and down. Now, this is a chicken and egg story that is this more fundamental or this more fundamental? We don't know. So usually before Casimir or before Bohr suggested that to Casimir, the idea was always to do this. You start from this and do the quantum. Basically, you do quantum mechanics, second order or probably higher order quantum mechanics, and get this effect of this interaction. But Casimir came and said that, okay, I'm not going to fluctuate this. I'm going to assume that these are fluctuating, even though there is no electric field in there, that is fluctuating. And he could get the same result in a very much more compact manner and much more suggestive that this is a 0-point energy. So that's the way to probably say it. But I don't think it has, because this is a perfect conductor and that's an infinity, that's why he had to take it. No, even if it was not a perfect conductor, you can get this. The result is more tedious, that's all, but it can be done even if it is not infinity. And then you can do it. Did I answer that question?
I guess Casimir, like the Casimir polder, the atom above a perfectly conducting plate was done before, right? A year before.
Correct.
And that was done with the full machinery of that quantum field theory, like
yes,
quantum electrodynamics, basically.
Mm-hmm.
Right.
Mm-hmm. Yeah.
So, is there cannot be some other field, why electric field or magnetic field, some other field that.
Oh, yeah. I mean, one can extend this. If you have charges that are oscillating, you create electric and magnetic field. But now you can think of masses that are oscillating, like mass is oscillating.
Yeah.
Then you talk about gravitational field, right? Yeah. I mean, any field in principle, you need a source and a response, right? And this idea, I think that's the basic idea of quantum field theory, that any source and field are related, and this effect will be there. And this is sum of, I mean, if you think of it in terms of quantum field theory, one can show that this is the sum of all the loop diagrams, all the polar or the charge polarization loop diagram, all of them, like 1, 2, 3, all the way going to infinity. So it's a non-perturbative effect. And any field theory in that sense will have this non-perturbative feature in it. So for example, I mean, very loosely speaking, when you have a black hole and you have a very strong gravitational field, it can create masses, I suppose, right? Like we already talk about photons being created there, that's the Hawking radiation, but we can also talk about masses being created because the gravitational field is so strong. But very loosely speaking, I don't want to claim that.
So
Is
any
it
field
Hawking radiation?
Sorry,
Sir.
I was just trying to make a comment. So it will show in any fields because it's a statement of boundary condition sensitivity to the vacuum, right? Essentially, you are changing the boundary condition, so the vacuum is changing. It's
yeah.
So
yeah, I would say yes. That's reasonable. Yeah.
Yeah. Okay.
Yeah. Correct. Like with the quantum fluctuations plus the boundary conditions gives you the idea. Yeah. But there, probably, yeah. I mean, I think in that black hole example, there is a field there. In that sense, it's not pure vacuum, right? So that will be more like a pair creation, which is called Schwindel's pair creation, because he was the first time to do that in electrodynamics. So yeah, so that will be the analog of pair production, correct? To the mass, like near a black hole. Yeah, maybe I gave a misleading comment there. Yeah, but
there is a point of view like Padmanabhan. You don't need quantum for a description of gravity, right? There is that point of view also.
I don't know. Yeah. I don't know.
What was the question?
It's not a question. What I'm saying is whether you need quantum description to describe gravity. That is the question.
Yeah.
That's not conclusive for some of, I don't know, I'm not an expert. For some people think you don't need.
Yeah, and maybe I can add one point here that okay. Yeah, can I take 3 more minutes? Maybe I'll come to that point, that is it quantum or not. So I think if I take a few minutes, it might help. Like, so parallel plates. So I promise I'll connect it with that. So parallel plates attract, right? So this is attractive. And Casimir in 1953 proposed that, let's say a simple charged sphere. So this is positively charged. And if we take simple electrostatics, this is an electron model. Like, let's think of an electron, right? There is a spherical charge there, so it should be repulsive. So there will be a stress on this. So this is the force or energy, let's say, energy associated with electrostatics. And that comes out to be E square in SI units. So that's 4 pi epsilon naught. And then there is 1 over 2 times the radius, right? That's the radius. So that's a force that is repulsive. So charges try to repel. But this is attractive now. So Casimir, this is Casimir himself, right? In 1953, he proposed that if this is attractive, this also we can presume that is attractive. So this will have an attractive force in here. They will balance out. So he presumed, so this is Casimir, let's say, that's equal to. And now this will be dependent on h bar c, right, over 2a. And there will be a constant there. So let me say, what should I call it? C, right? So there's some constant in there. So these two have to balance out, and it is clear that it will be E square over 4 pi epsilon naught over h bar c is equal to c. Right? In fact, that's the fine structure constant. So Casimir suggested that if you can calculate this Casimir energy for a sphere, then you can actually calculate, that's a way of calculating this fine structure constant. But just the disappointment was, like, so it was very hard calculation, and it waited until 1968, and this was Tim Boyer, and that is how I'll correct. But he showed that this C here is actually a negative number, right? So that's negative. So now you have Tim Boyer, so who showed that, who is the first person to actually do the sphere, and those are pretty much 2 solvable problems. If you want a pure electrodynamic problem which is solvable, parallel plates and a sphere. Rest everything, you have to be extreme, very extreme limits. Only then these are really doable, otherwise hard. And so this whole model fails, and Tim Boyer was a student at that time, grad student when he did this. Now Tim Boyer went ahead and started understanding these things, and in 70s and 80s, most of his work is that he said all of these effects, starting from blackbody radiation, Casimir effect, everything can be understood without introducing anything, any quantum quantum mechanical concepts purely by stochastic. It's called stochastic electrodynamics. But it's a very few people approach it that way. But I brought this up because he's one of the leading persons in that field, and then he went ahead and showed that most of these effects can be done without using any of those quantum features. So yeah, we should be open. That's the best I can say. Yeah. So
can I ask you something? I did not understand. Why should he assumed this electrostatic force is negative of what or Casimir force?
oh no, he didn't. Okay, so the
strain.
idea is so there is this charge that will be repulsive. This can be calculated as a stress, the electromagnetic stress. So that's a doable problem. This was done by Poincaré for the first time.
Yeah, that's okay. That was not my question. But there is a mechanical thing which supports that stress, right?
No,
Because that sphere is not a simple collection of charges, right? It has
let us say that this is a pure positively charged material that is building it.
I think what was the Casimir assumption? He was saying that Y is an electron stable.
Yes.
And the simplest picture he was thinking is that assume that electron is a spherical shaped object. So he was saying like it should be electrostatically, it should be like blowing apart, but it is not blowing apart. It's a stable thing. Maybe Casimir effect, like Casimir force is stabilizing it. That was his proposal.
No, I mean, we have some problem in assuming it because there are ions. If you take a real material, there are real conductor, there is ions, in that you assume free electrons, right?
True, true.
So when you stress it, a mechanical support also, which even if you don't assume Casimir effect, the thing will be equilibrium because whatever stress is created is balanced by the mechanical strain in the sphere.
Yes. So now I think the question could be just at a fundamental level, if we are talking about an electron, what force is that? Like, what is that mechanical force that is actually pulling it? It cannot be a string or anything.
No, that is the problem. An electron in a conductor is different from completely free electron.
So I think this is a free electron.
So the sphere is actually an electron.
Electron, yeah.
But free electron in quotation, right? Actually, it is an electron inside.
No, it is not a free electron in potassium or anything. It's just the question Casimir asked is, what is the structure of an electron? And assuming it is a spherical shell, then how it is stable?
In an abstract.
That's what I am asking. If you take a
like you are taking it to the real material, but that is not what Casimir asked in 1953 when he proposed that. He just said that, oh, this is single electron. There is one negative E charge on it. And assume that it is uniformly distributed like a sphere.
No, I am asking in a uniformly charged conductor. That's what you are saying.
A uniformly charged distribution of that one minus E on this one.
This is electron.
Okay.
So
electron in a
electron, that's it. This is an electron, and we are interested in asking what is the structure of an electron. So maybe I should not say
structure of electron. Oh, I'm sorry. Okay.
Yeah. So this is I think this is called the electron model. Poincaré called it. This was a big I think in 1900s, I think they worked a lot on this right before relativity. There was a lot of effort put into
okay. Now I got. I'm sorry.
Yeah. No. That's nice. So
no, that kind of thing has problem. Other aspect also.
But the hope was that by any chance, if this balances it, then, oh cool, then we have some understanding of that. But it turned out that it is negative, and that raised more questions now. Now, why is this negative? Like, this is attractive, why does sphere become repulsive? Is there any fundamental reason? So that's all I would say, in many ways, open questions. Mathematically very clear what is happening. We can tell, oh, this cancels that, and that's why it's happening, but that is not very insightful. So it's usually considered an open question as to why is the spherical shell repulsive over a parallel plates being attracted. So sort of interesting.
So okay, so if students or anybody wants to ask
Please.
questions on career opportunities,
Oh yes, so that,
yeah, so we missed that point. So if you want quick 1 or 2 questions, if you can ask, if you really want to know, you can ask. Any students who want to ask regarding the career opportunities, you can ask. Okay.
I can also promote. You can write to me if you feel more comfortable that way. No, what's my email address? And we also have SPIC Science Center, so feel free to come there and ask me questions there if you feel comfortable. But here, yeah, go ahead and ask questions if you.
Yeah, is there any question? Please ask. If there isn't any, so once again, let's thank Dr. K.V. Shajesh for his excellent lecture series. This was our first Blackboard lecture series also. Thank you for that. And once again, thank you very much.
Yeah, thanks a lot, Vishnu. Thanks, Krishna, for organizing this. And thanks to Radul. I think he was the one who was interacting with me. Thank you very much.